All right, okay, so keep in mind, okay, so for easy priority rule, okay, so that's based on atomic number. The higher atomic number, the higher priority, okay. So yeah, if the two higher priority groups on the same side of the bond, we call the Z, okay. If they're on the opposite side of the bond, we call the E, okay. And so yeah, there's situation, okay, so if the carbon, okay, so yeah, if the first layer, okay, so of the substituent group, okay, same, okay, so for example here, okay, so here, okay, the first layer all kind of CH2, 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 okay. So in this case here, yeah, you move to next level, okay, next layer, okay, to see compare the atom attached with the carbons, okay, and so until you see difference, okay. And for example, showed here, okay, so the methyl group has only hydrogen attached to it, and ethyl has carbon, okay, and then amine has nitrogen attached to it, okay, and then alcohol has OH group attached, okay. So in this case, priority increase in this kind of order, okay. All right, and give you guys one example, okay. Okay, CH2OH. All right, for example, here this molecule, okay. So yeah, we try to design easy for the middle CC bond, okay. All right, and if we look at these two individual carbons, okay, so we look at kind of last carbon first, okay. The first layer same, okay. So yeah, just the two carbons, okay, both are carbon, okay. And then yeah, we cannot distinguish which one kind of has higher priority, and then we move to next level, okay. Next level, okay, so yeah, the top only has hydrogen attached to this carbon, bottom has the carbon attached to this carbon, okay. So that means this one has high priority, okay. And similar thing, okay, so we look at kind of the right carbon, okay, so the top, bottom both connected with carbon, okay, but the top one has oxygen, okay, attached with this carbon, okay, and then bottom one only has carbon attached to it, okay. So the top one has high priority, okay. Right. So in this case here, this molecule should be E, okay. Okay, so yeah, high priority group on opposite side of the bond, okay. All right, so from now on, okay, so yeah, you need if there's the cis trans isomer for the cis bond, you need to give either cis trans assignment or give ED assignment. But yeah, note for this even increase, okay, the quiz 5, quiz 3 in this evening, okay. So if there's cis trans, you don't need to give the assignment, okay. But yeah, after quiz 3, okay, so you need to give assignment, okay. All right, and then yeah, next you guys take try, okay. Try to name this compound, okay. So name this compound, okay. Yeah. And so yeah, normally speaking, okay. So when you name one alkene, okay, or some kind of the compound contain a CC bond, okay. So yeah, you don't need to worry about kind of you easy cis trans very beginning, okay. You just kind of do the regular way like we did before, okay. And then yeah, in the end, okay. So you put EZ or cis trans before the whole name, okay. That's kind of full name. Right, so yeah, take a try, okay. So yeah, if someone like you can put the full name in the chat window, okay. Right. So while you're working on this question, okay, so yeah, a couple of things, okay, just one reminder, okay. So we'll have quiz 3 this evening, okay. So quiz 3 meaning carry the chapter 12, okay. So also there are some chapter 5 the materials, okay. And so I have actual office hour, okay, so just right after this class, okay. So once this class done, okay, so I will open the Zoom, okay, from 2 to 3, okay. So if you need help, okay, so please log in the Zoom, okay. And so I will also keep this Zoom open during the whole quiz period, okay, from 8 until 11, okay. So any questions, okay, so any problem, especially kind of technical problem, okay, please log in Zoom, okay, and let me know, okay. All right, anyone know the name for this one? Looks like this is hard one. Okay. For the molecular kind of the naming, okay, so pretty much you do the same thing like we did before, okay. So first find the highest priority functional group, okay. So that's the alcohol definitely, okay. All right, and then we need to find the longest carbon chain, okay. So with the OH group attached, okay. So that's has to be here. Okay, make sure that contain the CT bond, okay. All right, and then we need to take off this part first. Let's give the part name, okay. All right, so 5 carbons, okay, should be pen something, okay. Pentene, okay. All right, so you need to try to label the position number for the CT bond, okay, and also alcohol, okay. All right, so when we number it, okay, so we gave you the lower number for alcohol, okay, so that's 1, 2, 3, 4, 5. All right, and then that should be the 2 pentene, okay, 2 pentene, okay, so you can put the 2 between T and E, okay, so that's label the CT bond position, okay. And then should be 2 pentene O, okay, so but we need also give you alcohol position number, okay, so that's 1, okay, 2 pentene 1 O, okay. And in the end, okay, so we actually not in the end, okay, so next we take off 2 second group, okay. One is the isopropyl, one is the methyl, okay. So isopropyl, okay, so it has a low alphabetic order, okay, so we put the before methyl, okay. So that's 2 isopropyl, 3 methyl, 2 pentanol, okay. And we already know the steric country for the CT bond, and then we just do this, okay. So put the E in the parenthetic and then connect the with hyphen with the this whole name, okay. So that's the how do you give the full name for this compound, okay. All right, and then next rules about the CT bond, CO bond, and also CN bond and CN tri bond, and also CT tri bond, okay. So if we have those kind of the functional group, okay, attached to the CT bond, okay, how do we assign their kind of priority, okay? Priority is still based on the alphabetic order, the atomic order, okay, atomic order, okay. All right, so just write it down, okay. So if it's a CT bond, okay, so you treat it as the 2 carbon attached on the same carbon, okay, attached with this carbon, okay. And if you CC triple bond, okay, so you treat it as the 3 carbon attached to on the same carbon. And if it's the CO bond, okay, you treat it as the 2 oxygen attached to on the same carbon. And in that case, so if it's a CN triple bond, okay, you treat it as the 3 nitrogen attached to on the same carbon. Right. In this case, you can compare the priority, okay. Right. Give you one example, okay, so you know what I mean, okay. All right, CHO, that's aldehyde, okay. Right. For example, this molecule, okay, so we try to assign easy for the C bond here, okay, this C bond, okay. All right, so for that easy, okay, we have to look at the 2 carbon that are kind of the starting group, okay, on these 2 carbons, okay. All right, so we look at kind of left carbon, okay, left carbon, okay, so first layer, okay, so both carbon, no difference, okay. And then we need to look at kind of attachment on these 2 carbon, okay. For the top one, okay, top one you have kind of aldehyde, okay, so aldehyde we know that kind of the CO bond and H, okay. So that's we can treat this one as kind of 2 oxygen attached to the carbon, okay. Right, 2 oxygen, okay. And then for the bottom carbon, okay, so only one oxygen, that's alcohol, okay, and then another is carbon, okay. So that means here the yeah, this top substitute group has higher priority, okay. Right. And then we look at kind of the right carbon, okay. Right carbon, okay, so similar situation, okay. So yeah, we have carbon, okay, can note here the 12 difference, okay. And then we look at kind of the next level, okay. So next level, okay, this carbon, okay, has the two, yeah, the carbon attached to it, okay. So that's we treat that kind of see that one, treat that kind of just here the two carbon attached to it, okay. And very interesting is kind of bottom carbon, okay. So this carbon, okay, also has two carbon attached to it, okay. So we still cannot distinguish these two kind of which one has higher, okay. And then we move to next level, okay. So now we need to look at kind of this carbon, this two carbon, okay. Right, and then this carbon, okay, the top one still has the C double connect. That means kind of this carbon has two carbon attached to it, okay. And but the bottom carbon, okay, only has a hydrogen attached to it. So that means here the top branch has higher priority, okay. So that means here the two high priority on same side of that bond, okay. So that means kind of should be Z, okay. Right. And here are some small tips for you guys, okay. So very beginning, okay, student get always confused, okay. So E and Z, okay, and then make a mistake, okay. So right. So some kind of the small tricks for you guys, okay. So for E, okay, you can memorize it at kind of enemy, okay. And Z you can memorize as the easy. All right. So if we are two subgroups are easy to each other, okay, so they can be together, okay, on the same side of that bond, okay, so like here, okay. But if two subgroup kind of enemy to each other, they hit each other, okay, so they kind of push away from each other, okay, so that means kind of they have to kind of trans, okay. So that's will help you kind of memorize what the E means, what Z means, okay. Right. So just a little bit small tricks for you guys, okay. All right, okay. And then come to very important thing, okay, so the easy group priority, okay, so that's also this long name, okay, sequence rule, okay, are different from a functional group priority, okay. Functional group priority we learned in the chapter 12, also chapter 5, okay, there are big chart, okay, in the end of chapter, okay. Least kind of high priority, pretty much kind of capacity, okay. Lowest priority kind of the nitro, hydrogen, or kind of ether, okay. So that's the functional group priority, okay. Easy group priority, okay, so only based on the atomic number, okay, only based on atomic number. That's different from the functional group priority, okay. So we can do one practice, okay. So then you will know what's the difference, okay. Oxygen I already had, okay. Bromide and then in the end carbonic acid, okay. All right, so we have these five groups, okay, five functional group, okay. Right, so for you guys, okay, so you need first the write down the functional group priority, okay. Right, so we listen kind of from the lowest priority group to highest one, okay. Right, if someone like you can write it in kind of chat window, okay. Right, take a try, okay. So we have alcohol, alkene, aldehyde, bromide, carbonic acid, okay. So try to list their kind of priority group, okay. That's right, okay. So you need to list all of them kind of all five, okay. So from lowest to highest one, okay. Anyone, okay. So anyone want to take a try, okay. So list these five from lowest priority group, okay, to the highest one, okay. All right, so you don't put individual one, okay. So you put the all five together, okay. So from lowest to the highest one, okay. Some are labeled highest one should be carbonic acid, okay. So right, anyone want to take a try, okay? List all these five together, okay? From lowest to the highest. All right, pretty good, okay, so that's right, okay, so that's right answer, okay. Right. Bromide has a lowest party, the halide, okay, can only work as the prefix, okay, and then followed by alkene, okay, because alkene is kind of just the stated amount, okay, and then followed by alcohol, okay. Next is aldehyde, okay, and then okay, sorry, okay, so that's wrong, okay, should be like this. The highest one should be the capacity, okay. All right, so that's right, okay, good. Okay, so next, okay, so anyone can want to take a try, okay, try to assign easy part, okay. Again, if you like, you can put the answer in the chat window, okay. Anyone want to take a try, okay? No, okay. So for the cis trans easy relationship, I'll explain it later, okay? Don't worry, okay, don't worry, okay. So yeah, don't worry, okay. Anyone want to take a try, okay? So for the easy part, okay, so keep in mind, okay, that's correct, okay. So yeah, but you need at least all the five, okay, all five, okay. So easy part, okay, keep in mind, okay, based on only atomic number, lower atomic number, so yeah, the lower part, okay. That's right, okay, someone already said kind of the alkene is the lowest one, okay, that's right. No. Right. Right, what's next, okay? No, okay, so all right, okay, so now I go through kind of this one's a really hard one, okay, so yeah, a lot of students got confused this morning, okay. So easy part, okay, so yeah, that's only based on atomic number, okay, atom, okay, so yeah, alcohol is oxygen, alkene carbon, aldehyde carbon, bromide is bromide, okay, and then capacity is kind of capacity, okay, right, so you can see kind of the alkene, aldehyde, and then capacity, okay, connect with kind of the carbon, okay, so yeah, that here has low part, okay, and then followed by alcohol because that's oxygen, okay, and then it's bromide, okay. All right, so next we need to kind of these three guys, okay, alkene and also aldehyde and also capacity, okay. Alkene definitely lowest one because only connected by carbon, okay. All right, and next, okay, so both aldehyde and capacity, okay, connected by oxygen, okay, but aldehyde has two oxygen, okay, only two oxygen, one hydrogen, okay, and then capacity three oxygen, okay, so that means capacity has high part, okay. So overall, okay, so the order should like this, okay. Right, and then next you look at that should be alcohol, okay, and in the end, okay, bromide. Okay. Right. Again, okay, so yeah, easy kind of part, okay, you only need to look at the atom, okay. Atomic number, the higher atomic number, the higher part, okay. Okay, got it, okay. So this is the last year quiz questions, okay, not quiz, for probably the last year exam two questions, okay. So ask you kind of rank there kind of both the functional group part and also ED part, okay. So no difference, okay. So these two guys, okay, right? Make sure you know the difference, okay. All right, okay. So yeah, next is kind of another practice, okay. Ask you kind of design easy for the following molecule, okay. So yeah, this one actually we can do it one by one, okay. Right. So you just type your answer in the chat window, okay. Right. So for question A, okay. So it's the EOZ configuration, okay. Anyone want to try it? Okay. EOZ. Yeah. Anyone want to type the answer? No. Yeah, Z should be right answer. Z, okay. Right. Keep in mind, okay. Z is easy on the same side, okay. The high particle group on the same side, okay. So yeah, on the left high periodic group on the left carbon, high periodic group kind of carbon, okay, and then this methyl group, okay. On the right, okay, high periodic group, okay, is isopropyl group, okay. So we are both on the same side, okay. So it should be the Z, okay. Okay. So they should be Z, okay. Right. So what's the easy assignment for B, okay? Question B, okay. Anyone want to? All right, okay, okay, that's good, okay. So now you guys know it, okay. This one should be E, okay. So because the chloride has higher priority than the methyl, okay, and then methyl acyl group higher priority than hydrogen, okay. So these two on opposite side, okay, enemy, okay. So should be E, okay. Right. Come to the tricky one, okay. So for C, okay. For C, actually reality is kind of no, easy, okay. So no easy, okay. For C, okay. So no cis trans isomer, okay. Reason for that kind of we have two methyl group, two same functional group, okay, attached on the same carbons, okay. So there's no easy, okay. So this one just keep in mind, okay. Okay, so now let's try D, okay. So anyone what's the easy for this one, okay. Okay, so type your answer in the chat window, okay. For D, the E or Z. Okay, the right answer should be Z, okay. Because for the left carbon, okay, so this carbon, okay, you have bromide and chloride, okay. Bromide has higher atomic number, okay, higher atomic number, okay. So and then on the right carbon, okay, so this methyl group has higher particle group, than kind of this hydrogen, okay. So high particle group on the same side of the bond, we should kind of call it Z, okay. All right, so last one for question E or Z, okay. So anyone want to no. Okay, so E or Z. Right. So last one should be E. Okay, that's right. E. Okay. All right. So we look at kind of the left carbon. Okay. The propyl group has higher priority than methyl. Okay. On the right carbon. Okay. So this isopropyl group has higher priority than this methyl. Okay. And then these two high priority group. Okay. On the opposite side of the bond. Okay. So should be kind of E, okay. All right, okay. So that make sure you know how to do it, okay. Yeah. Why C is neither one, okay? Because the C for the left carbon, okay, you cannot design priority, okay. So left carbon, you have same attachment, okay, both a methyl, okay. So there's no higher priority, no lower priority, okay. So same thing, okay. So remember in the previous class I said, okay, so for easy assignment, okay, so you have to make sure that the two atoms attached to on the same carbon, okay, has to be different, okay, right? So if there are some same atom, okay, same kind of functional group attached on the same carbon, okay, so no matter what are other the group, what other carbons, okay, there's no easy, okay. My easy, okay, yeah. We do it here, okay. All right. So again, for easy assignment, you need to look at individual carbon first, okay? We first look at the left carbon, okay? Left carbon, okay? All right. And yeah, that's right, okay? Because it's symmetrical, okay? So no easy, no party, okay? So the same thing, okay? All right, okay. And then we look at the left carbon, okay? So left carbon, okay? So we have the isopropyl group, okay? Propyl group, okay? Higher parity than methyl, okay? Because this is the carbon connect carbon, okay? This one only hydrogen connect carbon, okay? Okay, here, okay. For the right carbon, okay, so there's a methyl group, this iso group. Iso group has high priority. All right, so because this one has the two carbon attached, this one only hydrogen, okay. So now two higher priority group, okay, on the opposite side of the bond, okay. So in this case, the should be E, okay, enemy, okay. Yeah. All right, so make sure you understand how to design EZ, okay. And when you go home, you can also practice the name of this compound, okay. So you can see for C, okay, there's no EZ, okay, so you don't need to give kind of the EZ, okay, for this molecule. Other you need to get, okay. All right, from now on, okay, so note the quiz 3 this evening, okay. So you need to give either cis or Z assignment for the older bond, okay. So if there's kind of cis trans isomers, okay. All right, here answer some student questions, okay. Some students say kind of it's possible we say kind of the E just the trans and then Z is cis, okay. So let's keep in mind, okay, so those are two different kind of naming system, okay. They are different, okay, they are different, okay. So sometimes kind of they give you opposite assignment, sometimes kind of give you similar assignment, okay. Give you one example, okay. So remember, yeah, the cis trans, okay, we look at kind of main carbon chain orientations, okay, and also like group on the same side or on the opposite side, okay. All right, for example, here, this molecule, okay. So if we want to assign just by cis trans, okay, we see kind of the two sub methyl group, okay, that's the like group, okay, on the same side of that bond, okay. So that should be kind of called cis, okay. Right. But if you want to assign EZ, you find a difference, okay. So right. So EZ you need to kind of the attachment on the individual C double carbons, okay. So here the higher particle group, okay, and then here's higher particle group, okay. Right. So on the left carbon, methyl higher particle, on the right carbon, bromide higher particle. So the higher particle on the opposite side, okay. So that should be E, okay. Right. So that means here the cis not necessarily be Z and the trans not necessarily be E, okay. And in exam quiz, okay, you can either use cis trans or kind of easy than kind of the bond, okay. But I encourage you guys here try to use easy, okay, because they're easy kind of the more general, okay. So it can handle all the situations, okay. So cis trans sometimes kind of the hard to design all the kind of the stereochemistry, okay. All right, okay. So things can get more complicated, okay. So if there's more than one double bond, okay. So and then if all these double bond, okay, so show the cis and trans isomers, okay, you have to give their all assignment, okay, right. And so if cis trans follow numbers, okay, and also you have to give kind of their location numbers, okay. That's means people know which is kind of cis with trans with E, which is Z, okay. Example showed here, okay. So this is dying, okay, dying, okay. So there are two theta bond, okay. The first theta bond, okay. So there's no easy, okay, because they are kind of the two hydrogen attached to the terminal carbons, okay. No easy, okay. But for the middle carbon, okay. So that's should be E, okay. So because kind of the trans, okay. So actually kind of the two hydrogen group on the opposite theta bond, okay. So should be E, okay. And then its full name should kind of E pentane 1,3 diene, okay. So because only one theta bond has the cis trans isomers, okay, you don't need to give location numbers, okay. But for the second question, okay, second kind of example, okay, so both double bond, okay, double bond, okay, has easy kind of the assignment, okay. For the last one, okay, should be kind of the E, okay, because kind of chloride is whole bond kind of on opposite double bond, okay. And then for the right one, okay, so that should be kind of Z, okay, because they are kind of cis, okay, you can see kind of on the same side, okay. All right. In this case here, when you name this compound, okay, so okay, so we will do this one first, and then we'll do okay. You need kind of label 1E3Z, okay, right? Because you have to label their kind of location number that people know which double bond E, which double bond kind of Z, okay. Right. For the first one, okay, so the two double bond, okay. So the left the cis double bond, okay. There's no easy, okay. So know that, okay. So because there are two hydrogen, okay, attached to the same carbon, okay. So there's no easy, okay. So no cis trans isomers, okay. Cis trans isomer has become of a different attachment, okay, okay, on both carbon, okay. But for the right kind of the theta bond, okay. So there's easy, okay. So that should be E, okay. So then we label E, okay. Don't need to give a location number, okay, because there's only one theta bond has the stereochemistry, okay. So another one has no stereochemistry, okay. So that people easy to understand, okay. All right. Okay, so give you guys kind of another example, okay. So this one gets more complicated, okay. That's OOET, okay. So ethoxide, okay. And then here's iodine, okay. All right. Okay, so we have this molecule, okay. So has three double bond, okay. We call it an alkene, okay. And then yeah, very beginning, okay, again you don't need to worry about the cis trans easy, okay. So you just do the regular way like we did before, okay, and then try to give their kind of the name, okay. All right, so first look at kind of which group has highest priority, okay. So we have the our halide, okay, and also the ether, okay. So those kind of lowest priority, okay. So and then in this case we need name this compound based on kind of the alkene, okay. So alkene, okay, so we found the longest carbon chain, okay, and then contain all three cis bond, okay. So that's what we call this way, okay. If you want to start from the bottom carbon, that's also fine, same thing, okay. So that's you need to take care of first, okay, this part, okay. Right, and then next, okay, so we need the give location numbers, okay. So we label the number the carbon chain, okay. So we need the number from the right to left, okay, because this the cis bond close to kind of the right end, okay. 1, 2, 3, 4, 5, 6, 7, 8, 9. All right. Okay, so that's here the noning something, okay. So 9 carbons, okay. So all right. So because there are 3 bond, okay, so we need to call it kind of triene, okay. So triene, okay, so we need the K to there's A between the noning and also triene, okay. Right. Okay, and then also we need to give their kind of location numbers, okay. So for the 3 bond, okay. So that here should be 2, 4, 6. Right. So number connected by a comma, and then number letter connected by the hyphen, okay. All right, okay. So that's here we down the kind of main carbon chain, okay, and then we take off here the 3 substitute, okay. So that's methyl, this is ethoxy, this is aldehyde, okay. So just here give their location number and then list them kind of alphabetic order before kind of parent name, okay. So ethyl is kind of ethoxy has a lower alphabetic order, okay. That's 3 ethoxy, and then followed by the aldehyde, okay. So that should be 7 aldehyde, and then the methyl, okay. So that's 2 methyl, and then that hyphen, okay, connect 2, 4, 6 non-triene, okay. And then that's we down the kind of just the carbon and also all atoms, okay. In the end, okay, so you need a label stereochemistry, okay, okay. So we have 3 alkene, okay. So 2 alkene, 4 alkene, and then 6 alkene, okay. And then for 2, okay, there's no easy, okay, those 6 trans, okay, because for 2, okay, so you have kind of 2 methyl group attached to it, okay. We already learned that, okay, so 2 same substance, okay, on the alkene, there's no cis trans, okay. So 2 you don't need design, okay. But here the 4 middle cis bond, okay, so the typical kind of the E, okay. Okay, so that's kind of some trans, okay. And then for the left kind of the cis bond, okay, so also E, okay, because the iodine has higher priority than the ethyl, and then this is kind of also higher priority than hydrogen, okay. So that's E, okay. Right, and then you need to add the stereochemistry assignment for these 2 alkene, okay, before the whole name, okay. So that's 4E, 6E, put in the parentheses, connected by hyphen, okay. So that's the full name for this molecule, okay. A little bit complicated, okay. So in exam quiz, okay, probably you won't get kind of so complicated kind of alkene naming, okay. But you do should say some kind of triene, diene case, so 2 bond case, so maybe I will show you kind of in the future exam quiz, okay. So make sure don't forget that are kind of easy case, so if there's one, okay. All right. And then next is the cycloalkene. Cycloalkene is kind of the cis bond in the ring system, okay. So normally speaking, if there are 7 or less the carbon in the ring, okay, only possibility is kind of cis, okay. So for example, cyclohexene. All right. So that's only possibility goes kind of cis, okay. So that's cis, okay. And the hard to get the trans, okay, because too much drink, okay. So the trans you have to go like this way, okay. So that's impossible for small ring, okay. And so yeah, in this case, yeah, if it's kind of the cycloalkene with 7 carbon or less, okay, you don't need the give their kind of easy element, okay, because that people know that has to be the 6, okay. But if we are 8 or more than 8 carbons in the cycloalkene case, so there's a possibility for the trans okay alkene case. So but very unusual, okay. Normally it's just kind of 6 alkene. So those here just keep in mind, okay. Yeah. All right, okay. So if any question, you guys can still type in chat window, okay. Right here we talk a little bit about the string, okay. So compare kind of stability of cis alkene and also trans alkene. Okay. Here we use the cis 2 butene, trans 2 butene as example. Okay. So string means any factor that destabilize the molecule by forcing its it to deviate from its optimal bonding geometry. Okay. So just destabilize the molecule. Okay. For example, the alkene should be 120 degrees, okay, trigonal planar structure, but here you force it kind of from 120 degrees, okay, that should be kind of called string, okay. Also similar thing for the tetrahedron, the geometry 109.5 degrees, okay. So if there's some very bulky group, okay, force it kind of away from 109.5 degrees, okay, that's what we call the string, okay. And then one of the most common string we call the steric string, okay. So that's kind of non-bonded atoms kind of force too close to each other, okay. So for cis alkene, okay, there's the steric string, okay. So for example, okay, so this the cis the 2 butene, okay, these 2 methyl group on the same side of the bond, okay, and then too close to each other, that kind of string, okay. So I made one model, okay, and then show you guys what this looks like, okay. Okay, here, okay. So this is alkene, okay. So you see kind of double bond, okay, and then this is cis alkene, okay. So 2 methyl group, okay, on the same side of the double bond, okay, and then this 2 methyl group, okay, right, too close to each other, okay, and then kind of we call the steric string, okay. But there's no such problem for the trans alkene, okay. Trans alkene, okay. So we put the methyl on the opposite side of the double bond, okay. All right, you see kind of still double bond here, okay, but the 1 methyl group, okay, is on the up, okay, 1 methyl group going down, okay. So there's the no kind of string, okay. Okay, so they're kind of far away to each other, okay. So that's means the trans alkenes normally more stable than cis, okay. Yeah, that's right. Okay, so sterical destabilize the molecule, destabilize molecule. Okay, so more string, more kind of unstable. Okay, more unstable. Okay, right. Actually, kind of people try to because searching to and trans kind of more stable than the cis alkene. Okay. And actually, kind of people did some kind of we call hydrogenation reactions. Okay, and just add a pair of hydrogen onto a cis double, okay, and then convert the cis alkene and also trans alkene both into the saturated butene. Okay, so I mean the cis the 2 butene. Okay, so here's the cis 2 butene, and then we transfer into kind of just add the hydrogen, okay, add hydrogen, okay, and then make it saturated, okay, and then it's become kind of butene, okay, saturated one, okay. And then people study kind of how much energy, okay, so released during this process, okay, and compare it with the trans alkene, okay. Right, that's trans alkene. Trans alkene, if you do the same reaction, okay, should be hydrogen, just hydrogen, okay, H2, okay. Right, and then you generate kind of same molecule, okay. Right, and then people find the cis alkene released more the energy, okay. So here, okay, that's the cis, okay, and then here the trans, okay. Right. The reason for that kind of the cis alkenes kind of less stable, okay, and then has higher energy, okay. And then when it go back to the saturated butene, okay, release more energy, okay. But the trans alkene kind of relatively more stable, okay, and then less energy, and then kind of release less kind of heat. Okay. All right. Okay. So now yeah, we little bit switch gear. Okay. So yeah, the two conformation. Okay. All right. So conformation is about kind of the different shapes. Okay. So by rotate one single bond. Okay. So yeah. Okay, keep in mind single bond. Okay. So that bond you cannot rotate. Okay. So that's why general kind of cis and trans kind of isomers. Okay. And then yeah, one compound can have the many kind of different conformations. Okay. So yeah. Right, so that's here the several conformations, okay, and so yeah, interconversion between the different conformation, okay, it won't break up the bond, okay, and then just here the happen kind of naturally at room temperature, okay. Right, example is here the for this here the we call kind of the still here the built-in, okay, right, and then we try to rotate here the middle CC single bond, okay, this bond, okay, and rotate for 180 degrees, okay. So pretty much here we keep here the left carbon, okay, no change, okay, and just here rotate here the right carbon 180 degrees, okay, and then we generate kind of new conformation for built-in, okay, right, and then you can see, okay, very beginning, okay, so for the right carbon, okay, the hydrogen kind of point towards you, methyl point away from you, and then hydrogen, okay, this hydrogen kind of in the plane, okay, but once you rotate 180 degrees, okay, so this hydrogen will going down, okay, but still in the plane. But this hydrogen, okay, so the wedge bond connect hydrogen, okay, going up, but the become kind of a dash bond, okay. And then this methyl group, okay, also going up, okay, but become wedge bond, okay, so 180 degrees, okay. So that shouldn't happen kind of well, just kind of naturally, okay, so at room temperature, okay. Right. Just one thing keep in mind, okay, so constitutive isomer and also stereoisomer, okay, so those are different molecule, okay, different compound, okay. So if you want to convert between isomers, okay, you break up the bond, okay. So that's different from kind of conformation. Conformation kind of same molecule, okay, so just kind of rotate by single bond, okay. And so here's the one way to draw the different conformation for one molecule, okay. So just here use the wedge dash bond, okay. So you just kind of rotate 180 degrees, okay, show the kind of wedge become dash become wedge, okay. And another way to show the different conformation of the alkenes, usually we call the Newman projection, okay. So Newman projection, okay. So Newman projection, okay, so we just kind of try to see the molecule in kind of from the two carbon, okay, so okay, so we draw like this way. So here I use I think as example, okay. Hydrogen. Right, so left carbon, one hydrogen in the plane and one hydrogen going away, one hydrogen point towards you, okay. And then for the right carbon, okay, similar thing, okay. So one hydrogen kind of going up, okay, and then one hydrogen going away, and one hydrogen point towards you, okay. When you draw the Newman projection, okay, so you need to put your eye, okay, just look through these two carbons, okay. So you put your eye like this, okay. Like this, okay. And then the front carbon, okay. Right, the front carbon, okay. So we use kind of one single point, okay, indicate the front carbon. Right, single point, okay. And then this bar carbon, okay. So the front carbon is kind of the carbon close to your eye, okay. Bar carbon is kind of a carbon far away from your eye, okay. We use one circle represent kind of bar carbon, okay. Okay. Next, okay, we can add attachment, okay. Right. So for the front carbon, okay, so there's one hydrogen going down, okay, and then this hydrogen, okay, so should be on your left, okay. So this the dash bond connect hydrogen, okay, on your left, okay. This hydrogen, okay, so should on your right. Okay. Right. And then we can do the bar carbon. Bar carbon, okay, so also has three attachments, okay. So there's one hydrogen going up, okay, that's this guy, okay. And then one hydrogen kind of goes to your left, okay, so that's here. And then one hydrogen goes to your right, okay, that's here. Okay, so that's we have one of the Newman projection for this the built-in. Okay, so that's how do you convert the wedge dash bond to the structure to Newman projection. Okay. Right, and then you can draw many kind of the Newman projections. Okay, depending the what's the structure. Okay, so here I have to kind of show you the model again. All right, so that's Athene. Okay. Okay, yeah. All right, and then when you draw Newman projection, okay, so you need the look here, that's your guys' eye, okay? So look from this carbon to the back carbon, front carbon, back carbon, okay? And then let's try to do this, okay? Okay, all right. Okay, and then there are the thorough conformation, okay? So the first one, okay, so just like this. Okay. So first one case where all the hydrogen kind of far away to each other. Okay, there are the 60-degree kind of dihedral angle. Okay, so okay, 60-degree. Okay, and this one we call the staggered conformation. Okay, another conformation. Okay, we rotated the bicarbon. Okay, so bicarbon this one, like 60 degrees. Okay, and then pretty much all the hydrogen kind of overlap to each other. Okay. Okay, so this one on the top of this one on top of this one on top of this one. Okay, so this conformation we call the eclipse conformation. This one has the higher energy and the less stable. Okay, so if we want to use the Newman projection. Okay, so that should be kind of staggered conformation. Okay, because the front carbon and front hydrogen and back hydrogen kind of the dihedral angle. Okay, dihedral angle is kind of 60 degrees. Okay, so that's here called staggered. Okay, and then if we let's try. Okay, so we just here the rotated for example, it's kind of rotated front carbon. Okay, so like here 60 degrees. Okay, so we just rotate like this way. Okay, so front carbon. Okay, so this hydrogen goes here, this hydrogen goes here. Okay, and then we generate kind of the eclipse structure. Okay, so all the hydrogen goes here, here, and here, and then the back carbon no change. Okay. Okay, so this one, okay, because of the overlap of all hydrogens. Okay, so we can call it kind of the eclipse. Okay. Right. So eclipse the hydrogen kind of the dihedral angle. Okay, so dihedral angle is 0 degree. Okay, and clearly you can see kind of the eclipse kind of the last stable. Okay, so they have certain string between the two overlapped the hydrogen CH bond. Okay, and this string we call the torsional string. Okay. SH. Torsion string. Okay, so that's the second types of the string we learned so far. Okay, the first we call the steric string. Okay, so the two non-bounded kind of group of atom kind of too close to each other. Okay, so the second type we call torsion string. Okay, only for eclipse conformation. Okay, so that's the too close to each other. Okay, and here's kind of something I just told. Okay, so staggered conformation, the CH bond kind of the front carbon and the far away part from the back carbon. Okay, 60 degree the dihedral angle. Okay, eclipse. Okay, so just 0 degrees. Okay, and then afterwards you can analyze the energy with the dihedral angle. Okay, so right beginning we have this the conformation. Okay, that's staggered. Okay, so the 60 degree dihedral angle. Okay, we rotate this case kind of the back carbon. Okay, so 60 degree each time. Okay, so we can kind of eclipse structures. Okay, higher energy. Okay, and then we further rotate the 60 degree. Okay, we generate kind of another staggered conformation. Okay, so last energy. Okay, this processor can go ahead kind of full circle. Okay, 360-degree kind of rotation. Okay, 3 eclipse structure higher energy and 3 staggered conformation at lower energy. Okay. And then situation can get more complicated if we put other attachment on the kind of ether case, replace the hydrogen with kind of bulky group like bromine. Okay. So that's we'll talk about in the class on Wednesday. Okay. All right. Okay. So that's we done the class today. Okay. So any questions? The answer is yes. Okay, so actually kind of trade bond and that bond kind of also work for but there's no conformation. Okay, so because especially on the double bond case, so you cannot rotate double bond case, but you can show the 3-dimensional structure okay of double bond case, so alkene and alkyne case. So by Newman projection. Okay, have a good day. Okay, you too. Okay, that's true. Okay, so So for the Newman projection, okay, each time you can only look at 2 carbons, okay, each time 2 carbons, okay. So but you can switch wing angles, okay, look at another 2 carbons, okay, draw new Newman projection, okay. So only 2 carbons, but more than 2 carbons also work, okay. But you have to change the view, okay, draw the new one, okay. Stop the recording.